So we learned about Boyle's, Charles, and Avogadro's law, which all said that either volume was inversely proportional. This little sign, instead of being an equal sign, because it's not equal to 1 over pressure, we're saying it's related to 1 over pressure. Volume for Charles' law is related to temperature, right? As volume goes up, temperature goes up. And for Avogadro's number, volume is proportional to the amount of moles. So if we put all those together where we solve for volume on one side, we can do pressure on the bottom, temperature, and moles on the top. And they're related, which means in order to get an equal sign, we need to find a constant that relates them all with an equal sign. So we can get that actually. They determined that that constant is equal to, not negative, but equal to 0.0821 liter atmosphere per mole Kelvin. And so we reorganize it to get this equation. Pressure times volume equals moles times the proportionality constant times the temperature in Kelvin. So this, our constant here, has all of the units of all of those variables in it, which will cancel out as we need it to. So let's practice with it. We have that calcium carbonate, which is a solid, is a principal compound in limestone. It decomposes upon heating to calcium oxide and carbon dioxide. A sample of limestone is decomposed and carbon dioxide is collected in a 250 milliliter flask. So let's highlight that. 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius. So we want to know how many moles of CO2 is there. So we're going to collect our variables. We have our volume equals 250 milliliters. We have our pressure equal to 1.3 atmospheres. Our temperature equal to 31 degrees Celsius, and we're trying to solve for moles. So the first thing we need to do is get all of our units in the correct unit. So we want our milliliters to go to liters. So we're just going to divide by 1,000 milliliters per liter. So we get 0.250 liters of CO2. Atmospheres is the correct unit for pressure, so that's good. And then we're going to add 273 to get into Kelvin, so we get 304 Kelvin. And now we can plug in. So we're going to use PV equals nRT. We're solving for N, so we're going to divide by RT on both sides. So we get N equals PV over RT, and now we can plug in our numbers. Pressure is 1.3 atmospheres. Volume is 0.250 liters. R is our proportionality constant, 0.0821 liter atmosphere per mole Kelvin, and our temperature of 304 Kelvin. So let's see how our units cancel out. We have our atmospheres canceling out atmospheres, liters canceling out liters, Kelvin canceling out Kelvin, and we're left with moles in the denominator. So a denominator of a denominator becomes a numerator. So that's good. We get our units of moles on top. So we can plug that calculation in, and we get 0.013 moles of CO2. Okay, so I love the ideal gas law because it's so straightforward to plug in. The hardest part, I think, is this initial part where we had to convert units. All right, tennis balls are usually filled with air or nitrogen gas to a pressure above atmospheric pressure to increase their bounce. If a tennis ball has a volume of 144 centimeters cubed, and remember that's the same as a milliliter, I'm not dividing, but it is a milliliter, and 0.3 grams of nitrogen gas, 0.33 grams, what is the pressure at a temperature of 24 degrees Celsius? So we have our volume equals 144 centimeters cubed, which is a milliliter. One less conversion to do if we can keep that in mind. We have our amount of moles. Well, we have our mass, which equals 0.33 grams, and we can get moles from that. And then our temperature is 24 degrees Celsius, and we're trying to find pressure. All right, so we're going to do our conversion. We're going to go milliliter to liter like we did earlier, and we get 0.144 liters. We're going to convert our grams to moles. So for nitrogen gas, so this is N2, we need to make sure we do the whole molecule, which is 28 grams per mole. So we divide 0.33 by 28, and we get 0.0118 moles. And then we're going to add 273 to 24, and we get 297 Kelvin. All right, so let's plug in PV equals nRT. We're solving for pressure, so we're going to divide both sides by volume. So we get pressure equals nRT over V. Plug in our numbers, 0.0118 moles times by proportionality constant, 0.0821 liter atmosphere per mole Kelvin. Let's scooch over, and the temperature being 297 Kelvin. And then we'll divide by our volume, 0.144 liters. So let's check out how our units cancel. We have moles canceling out moles, Kelvin canceling out Kelvin, liters canceling out liters. Whoops, and we are left with atmospheres on top, which is great. So once we plug in all of those numbers, get our calculation out, we get pressure equals 2.00 atmospheres, which is good because it did say it was higher than atmospheric pressure of 1, so that makes sense. This problem uses some combined gas laws, so some of those individual ones, but combined. So not all of them in the ideal gas law, but similar. So it says an inflated balloon has a volume of 6 liters at a sea level, which is 1 atmosphere. So let's just start to combine that. So we have volume 1 equals 6 liters, and pressure 1 equals 1 atmosphere. And it's allowed to ascend until the pressure, so pressure 2, is 0.45 atmospheres. During the ascent, the temperature of the gas falls from, so T1 is 22 degrees Celsius, and T2, it goes down to negative 21 degrees Celsius. So calculate the volume of the balloon at its final atmosphere or final altitude. So we want to find V2. There are a couple ways that you can approach this problem. Since we know that we have an inflated balloon and it is closed, we know that the amount of moles is going to be constant. We also know in our gas law that the R value is a constant. So this isn't changing and either of these are changing. So we can do PV equals nRT, and keeping in mind that these two things are constants. And just like we did earlier with the individual gas laws, we can set the whole thing equal to the constant. So what we'd get is PV over T, because we're going to divide T over as it's changing, equals a constant. And since it's equal to a constant, if we change any of these variables, they're going to need to shift in order to keep each other constant. So we could do P1 V1 over T1 equals P2 V2 over T2. And you can look up combined gas laws on YouTube and Khan Academy and find out other ways that people do this and solve for that. You could also solve for N under the first conditions, right? That's something we don't know. And then plug that in here to solve for V2. So there are a couple different ways you can do it, and that's where chemistry can kind of be creative in how you solve problems. If we use this equation here, we're going to solve for V2. So we're going to put our initial pressure of 1 atmosphere, our initial volume of 6 liters, and our initial temperature, we need to add 273. So we'll get 295 Kelvin. And I'm going to also add 273 to negative 21 degrees Celsius. And that's going to give us 252 Kelvin. All right, so anyway, for conditions 1, 295 Kelvin, that's going to equal our second pressure, which is 0.45 atmospheres, times by our volume, we don't know, divided by our new temperature, 252 Kelvin. So since we want to solve for V2, I'm going to multiply. I need to multiply by 252 Kelvin to both sides. So that cancels out. And then I'm going to need to divide by 0.45 atmospheres to both sides. So then what you get is your volume is equal to this long equation. So we can multiply the whole top, divide by the whole bottom. And when you end up doing that, I want you to plug that in your calculator to see what you get. Make sure you're not having any calculator errors. And you should get 11 liters. We can also determine the density of a gas using the ideal gas law. If you remember that density equals mass over volume. So what we want to do is get the ideal gas law, which is PV equals nRT, looking somewhat like mass over volume. So when I see mass, I also think of kind of like moles, right, an amount. And then we have volume here. So if we rearrange the ideal gas law by getting volume over here, so divide by volume, and getting this whole thing, the N over V by itself, so also dividing by RT to both sides, then we end up getting N over V equals P over RT. So already this is looking very similar to the density equation, but we need to get our moles into mass. And so in order, if I have an amount of moles of something and I want to get it into mass, what I'm going to do is I'm going to take the molar mass and I'm going to multiply. So if I had like, let's say it was like H2, right? I'd have 2 grams per mole. So I'm going to take my amount of moles that I have and I'm going to multiply it by the molar mass. So moles times molar mass equals a mass. So what I'm going to do to this whole equation on this side is I'm going to multiply both sides by molar mass, or capital N. So when I do molar mass times moles, I get mass. And now we have that the density, which is mass over volume, equals pressure times molar mass over RT. And you might be wondering, why did I multiply molar mass by both sides? Well, the ideal gas law is good on its own. If I multiply molar mass on one side, I have to do it to the other one to even it out. So we end up getting that M over V, which is density, is equal to the molar mass times by the pressure divided by RT. So I want you to have that circled in your notes. We could also solve for the molar mass using the density and find the molar mass if I have the information for my gas. So if I took my density equation here and I did density equals mass times pressure over RT, I could solve for molar mass by dividing by pressure, multiplying by RT, right? So then RT cancels, pressure cancels, and what I get is molar mass equals the density times RT over pressure, or if I expand it as density is mass over volume times RT over pressure. So both of these are good. If it gives you density, you'll use that one. If it gives you mass and volume, you'll use that one. So let's practice. I want to find the density of carbon tetrachloride, which is CCl4, at a vapor, or when it's in the vapor phase, at a pressure of 714 torr and a temperature of 125 degrees Celsius. So let's use the density equation. Density equals molar mass times pressure over RT. So the molar mass of carbon is 12, plus we have 4 chlorines and their molar masses are 35.45. This gives me a molar mass of 153.8 grams per mole. All right, and then we know our R is 0.0821 liter atmosphere per mole Kelvin. A good reminder of our units. So our torr needs to go into atmosphere. We haven't done that yet, but as a reminder, we have 760 torr is 1 atmosphere. So when we divide that over, we get 0.939 atmospheres. And then we're going to add 273 to get Kelvin, and we end up getting 398 Kelvin. So now we can plug in density equals 153.8 grams per mole times our pressure, 0.939 atmospheres, divided by R, which is 0.0821 liter atmosphere per mole Kelvin, and then we have our temperature of 398 Kelvin. So let's see what happens to our units. We have mole on the denominator, canceling out the denominator mole. We have atmosphere and atmosphere. We have Kelvin and Kelvin. So what we're left with here is grams per liter, which is what we will use for the density of a gas. It is measured in grams per liter because it's it has such a low density. Grams per milliliter would be such a tiny number. So we'll plug that all in, and you should get 4.42 grams per liter, which is the mass over the volume. For this next problem, we have the molar mass, the average molar mass of the atmosphere at the surface of Titan, which is Saturn's largest moon, is 28.6. So the molar mass is 28.6 grams per mole. The surface temperature is 95 Kelvin. That's pretty cold. And the pressure is 1.6 atmospheres. Assuming ideal behavior, calculate the density. So here we have the molar mass in the equation. So we can use density equals pressure times molar mass over RT. Plug that in. We have our pressure at 1.6 atmospheres. Molar mass, 28.6 grams per mole, divided by R, 0.0821 liter atmosphere per mole Kelvin, and temperature of 95 Kelvin. All right, just like before, same kind of equation. We're going to have our atmosphere, mole, Kelvin, and we're left with gram per liter, so that's great. We plug that equation in, and we get the density of the surface of Titan is 5.9 grams per liter. Now we're going to practice calculating the molar mass of a gas. In this first problem, we want to find the molar mass of a dry air. It has a density of 1.17 grams per liter, and the temperature is 21 degrees Celsius, and the pressure is 740 torr. So we have some unit conversion to do. We need to add 273 here to get 294 Kelvin. We need to divide by 760 torr per atmosphere, and that should give us a value of 0.9737 atmospheres. All right, so we're given the density, so we want to use the equation that for molar mass that involves density. So we know that the molar mass with density is density times RT over pressure. So we can plug that in. Density is 1.17 grams per liter. R is 0.0821 liter atmosphere per mole Kelvin. Temperature is 294 Kelvin, and our pressure of 0.9737 atmospheres. Check our units, because it's always a good idea to. We have liter canceling out that liter, Kelvin canceling out the Kelvin, atmosphere canceling out atmosphere, and we are left with grams per mole. Great, that is the molar mass. So we could solve for this. Molar mass of dry air is 29.0 grams per mole. And that's pretty close to nitrogen, which is 28 grams per mole, and nitrogen makes up like 78% of our atmosphere, so this makes sense. Always do a logic check. Okay, in this next problem, we have a large evacuated flask. Initially has a mass, so we have a flask. I'm going to draw it. Mass of the flask is 134.567 grams. How convenient on those numbers. When the flask is filled with a gas of an unknown molar mass, it has a pressure of 735 torr, and it has a temperature of 31 degrees Celsius, and its new mass of flask plus gas is 137.456 grams. When the flask is evacuated again and then filled with water at the same temperature, its mass, so mass of flask plus water, is 1,067.9 grams. And here's the density of water. So this is a much more complicated problem because we have, this is what you would see in a lab. So let's just keep it straight. We need to find out the molar mass of the gas. So we know that the molar mass of the gas is going to be equal to. Now we're not given any densities. We are given a bunch of masses, temperature, pressure, but no density. So we're not going to use the density equation. We're going to use the one that tells us that the molar mass is the mass of the gas times by RT over the pressure of the gas times the volume of the gas. All right, so we'll plug that in, the mass of the gas. So we know the mass of the flask is pretty heavy, and the mass of the flask plus the gas. So to find the mass of the gas, we need to do 137.456 minus 134.567 to get the mass of the gas. And that ends up giving us a value of 2.889 grams. So that is the mass of the gas. Now we know R 0.0821 liter atmosphere per mole Kelvin. And we know the temperature is 31. We're going to add 273 to get 304 Kelvin. All right, they also give us the pressure. We're down in pressure now in torr. So we're going to divide by 760 torr per atmosphere. And our pressure value ends up being 0.967 atmospheres. So plug that in, 0.967 atmospheres. And then our volume. So this is where we need to be creative. So they filled it all the way up with water and measured the mass. So we know the empty flask and the flask plus water. So we could find the mass of the water that's in there. And we can find that that's going to be equal to the flask and the water. So 1067 grams minus just the flask by itself. It's 0.9. And then it's 134.567 grams. So we end up getting the mass of the water being 933.3 grams. And we need to find its volume from there. And they did give us the density of the water. Now you might have been confused and been like, okay, that's density, but notice that's the density of the water, not the density of the gas, so we can't use it in our other equation. But we can use it here and do some dimensional analysis. We can say that the density of the gas is 0.997 grams per milliliter. And then we could get that over into liters, saying 1,000 milliliters is a liter. So we could take our grams into milliliters using the density of water and milliliters into liters. And that ends up giving us a volume of 0.936 liters for the volume of the container, which was filled with water. So we'll plug that down here. 0.936 liters. That was a very complicated way. You might be annoyed. I get it. But we can plug it in now. So all that works. So I would just tackle each variable by itself, and slowly but surely you'll have dealt with all of the numbers. So when you plug that in, we get the density of this gas, the molar mass of the gas to be 79.7 grams per mole. The last thing we can do with the ideal gas law is go between, we can use stoichiometry. So we can use gas data to find out how many moles of gas we have in a chemical reaction, right? So I could have A plus B goes to C, and they're all gases. Let's say I have 2C. And so then what I can do is find the moles of one of the reactants, let's say it's A, then use some stoichiometry to go into another gas, or a non-gas, it doesn't have to be gas, but we could use stoichiometry to go to another compound and then use the other variables, whether it's molar mass or temperature, pressure, and volume, to go into another variable we might want. So basically we're just saying ideal gas law is another way to go to moles, just like we can use molar mass to go from grams to moles. We could use pressure, volume, and temperature to go to moles using ideal gas law, and then stoichiometry from there. Okay, so let's practice that. We have automobile airbags are inflated with nitrogen gas generated by the rapid decomposition of sodium azide, which is NaN3. Okay, here's the chemical reaction. We have 2 sodium azides, which is solid, going to 2 sodium solids, and 3 nitrogen gas molecules. If an airbag has a volume of 36 liters, so volume equals 36 liters, and is to be filled with nitrogen gas at a pressure of 1.15 liter atmospheres and a temperature which is 26 degrees Celsius, we want to find how many grams of sodium azide must be decomposed. And so this is all for when we have nitrogen gas. So we have pressure, we have volume, we have temperature, we can find moles. So we're going to do PV equals nRT. We are going to solve for the moles. We know pressure, we know volume, we know temp, and R. So we're going to solve for moles. We're going to divide by RT on both sides. And we get the moles of nitrogen gas equals pressure times volume over RT. So then I'll plug in the values. We get our pressure of 1.15 atmospheres times by our volume of 36 liters divided by 0.0821 liter atmosphere per mole Kelvin. And our temperature is 26 degrees Celsius, so we're going to add 273 to get 299 Kelvin. So we'll have 299 Kelvin. So we get here that our moles of nitrogen gas, when we plug all of that in, is 1.7 moles of N2. But it doesn't care about that. It wants to know how many grams of sodium azide do we have. So we're in moles of nitrogen. We need to get to moles of sodium azide. So I can say, use my chemical reaction to go moles of nitrogen gas to moles of sodium azide. Look at our stoichiometric coefficients. 3 for nitrogen here, 2 for sodium azide. And then last step is we're in moles of sodium azide, but we want to go to grams. So we're going to add our mass of sodium and 3 of nitrogens, and that gives us a molar mass of 65 grams per mole. So our moles cancel out of nitrogen, moles of sodium azide cancel out, and we're left with grams. So what we end up getting when we plug all of that in is that we need 72 grams of sodium azide in our airbag for it to inflate to the volume we want it to. So let's do another problem. In this one, it says the first step of an industrial process for making nitric acid, ammonia reacts with oxygen. So here's ammonia reacting with oxygen in the presence of a catalyst to form nitric oxide and water vapor. How many liters, so we want the liters of NH3 of ammonia at temperature equals 850 degrees Celsius and pressure equals 5 atmospheres, are required to react with 1 mole of oxygen. So we have moles of oxygen is this reaction, and so it's 1 mole. All right, so what do we know? Well, we already know moles of oxygen, so we can just start right there. We could do some stoichiometry. If it gave us grams of oxygen or gave us some other conditions, maybe it gave us the pressure of oxygen in this, like the partial pressure, which we're going to learn about next, maybe it gives us that, but it didn't give us the moles, so that's nice. We have the moles of O2. Now before we move forward, I just want to quickly add 273 to this before I forget, and we'll get a temperature of 1123 Kelvin, so very hot. So we have 1 mole of oxygen. Let's go straight in and say for every 5 moles of oxygen, we have, we're going to ammonia, so we have 4 moles of ammonia. So our moles of ammonia in this case are 0.80 moles. All right, now that we have the moles of ammonia, we can find the volume. We can use the ideal gas law. We know N of NH3. We know pressure and temperature, so we can find the volume, which is what we are searching for, of ammonia. So I could do PV equals nRT. Solve for V, so we're going to divide over by P. So the volume of ammonia is going to be the moles of ammonia, 0.8 moles of ammonia times by the ideal gas law constant times by the temperature, 1123 Kelvin, divided by the pressure of the container, so it is 5 atmospheres. Okay, so we just plug it in, and we get 14.8 liters.